everyone, my name is Chang Sun, and welcome to Women Data Science 2022 Maastricht Conference video series. Like most WIS worldwide conferences that took place in March this year, we were online. The WIS Maastricht Conference featured keynotes, technical talks, panel discussions, and many more interesting things. Dr. Zinger gave the first keynote in the WIS Maastricht Conference 2022 on the topic of where are AI-driven decision support systems in healthcare. Please keep watching.
Sveta has her research interest in digital image processing applied in healthcare. She studied her PhD in Paris, in France, and then she continued postdoc and with different other projects. She published more than 180 papers, and then she also established an Elsevier journal in computer methods and programs in biomedicine update, for which she's an editor-in-chief. So I'm really looking forward to see her talk, and I give the floor to you, Sveta.
So welcome again to my talk today. I would like to talk about decision support systems in healthcare, and they are currently AI-driven, and this will probably stay for a while. So I wanted to highlight some points that are related to these developments. Well, I don't need to tell more about myself. I think the only thing that I can add is that I'm an engineer. I worked more than 20 years in digital image and signal processing, and starting about 10 years ago, I concentrated more and more, and now fully, on healthcare applications in signals and images. One of the reasons for that for me was that, well, at first I believe there is a lot of work to do there. And at second, I think it's one of the most peaceful applications of engineering you can have. And I think peace is a good idea. So let's take a look at what we have in terms of image analysis in healthcare a little bit. So at the moment, imaging is key in many diagnostic and treatment procedures. You can see images being used in many domains like oncology, neonatology, that's about babies, cardiology, neurology. We can think about those big machines like CT, MRI, also small machines like ultrasound. So making images now is a part of clinical practice. The next step after making the images is, of course, interpreting them. So someone has to look at them and say what the diagnosis is or what the treatment should be, etc. So that's what we call analysis, basically. That's all clear. In principle, you can say, well, we have images, we have people who can analyze the images, so there is basically no problem. It's true, at least partially, because actually, if you go to a hospital now, that's what you will see: imaging machines and people analyzing the images. In the same time, if you look at the scientific research directions, you will see a lot of image analysis with AI, with deep learning, with all kinds of attempts to make this analysis automated. Why is that? Well, looking at those images, inspecting them, or treating videos of medical data is a very tedious work. Sometimes it cannot even be performed, at least not in reasonable time. So obviously that people are taking AI and trying to find solutions. There are more powerful methodologies coming in medical imaging. They include multidimensional signals. They include huge data volumes. So think, for example, about finding an instrument like a needle in a 3D ultrasound data volume. How can we do that? Well, we can go through all the slices of that volume, but if we need to do it real time during intervention, which is actually the case, there is no way that a very well trained doctor can do that. The same goes for example, for neurology. When we have MRI images of brain, we want to check intensities, which correspond to some biological processes in a particular brain area. So that area is represented again in a number of slices. a human inspection will probably not help there. Another example is when we want to do a disease development prediction, like a disease course prediction. For example, saying if someone will have depression 1 year from now. This is at the moment not possible. But then we are talking about longitudinal data analysis. Again, for a single human or even multiple ones, it is not something that they can do thanks to training or just very heavy hard work. So obviously AI is there, image analysis needs help, and healthcare can profit from it. Here I can show you an example of what is done a lot in medical image analysis, and that's segmentation. So finding a segment, a piece of an image, which corresponds to what you are looking for. Can be an organ, can be a region, a cancerous region. Segment can be meaning multiple things, but basically what we are doing, probably you can see now my pointer, so you are finding these blue lines that have to show that, okay, inside we have, in this case, something bad, and outside something good. And these are microscopic images, so basically you are looking more or less at cells here. So finally, hundreds, I think thousands of papers are dedicated to drawing these lines. So that's what medical image analysis is doing a lot. And you can also see in this slide here, metastasis, here normal. So we want to make that decision. I will come back to this example later. But the questions can be much more complicated to solve. So not only segmenting and finding the right border, but for example, helping the doctor with a diagnosis. Here in Eindhoven, where I work, we have quite a lot of people with autism. Autism can be found by highly intelligent people. This is called then Asperger syndrome. There are many of such people in Eindhoven, so many that even we have a separate school for them, for children and teenagers. So having a diagnosis of autism is a big step, because a child can even be removed from regular education and be put in a special education, and it's also a stigma in some cases. So you know that basically, you probably know that autism is characterized by just some behavioral changes. So there is no trauma, there is no wound, there is nothing wrong in the structure of the brain in principle, but these are different children. So the question is how to provide a diagnosis. The current way the diagnosis is provided, so that's a life-changing event, as such a diagnosis in principle, it's purely subjective. So there is no test, no medical examination that can be performed objectively and help the diagnosis. It's simply the opinion of the doctor based on a number of talks, observations, questionnaires, looking at genetics of the child, because autism is a genetically transmitted disease. So that's at the moment, that's a issue in neurology, how to diagnose autism and how to make it objective. We were working several years on that, and we actually took brain scans of a group of teenagers in a specialized school, and we also looked at brain scans of teenagers who are not diagnosed with autism, and then using multiple types of features, and very briefly, they are structural, functional, affective connectivity features. So we were creative in looking at what we can extract from the data, including the temporal components of the MRI scans that we could have. We built a framework basically for diagnosing it. So we went from the situation when we have only subjective diagnosis possible to the situation when we can have a classifier that gives you around 85% security that you are having here a person with autism. We would prefer, obviously, to have 100%. So such research is not fully done, I think, yet. But we obviously see how far we can go if we are smart in taking AI and smart in data science. So I just mentioned AI. So the question is, what about it now in healthcare? Are we there? Do we need more? What is the situation? Well, um, there is a lot of evidence that AI can help to support decisions of medical doctors. I am an editor in chief of a journal on computer methods in biomedicine, and I can say that there are really hundreds of papers, I think worldwide thousands of papers where potential of AI is shown. Also, real-time assistance based on AI is now possible given the developments in hardware. In the same time, we all know that in clinical practice, there is very, very little AI support. If again you are in a hospital, well, I hope you are not often there, but you can see still the systems that are 10 years old, that the system or more years old, that um, we are all dependent on the eyes of a doctor. Support is very limited, and I also, because I of course deal with doctors regularly for my work, I even know that when AI-based systems arrive, they try to switch off the kind of smart parts of them because those parts are still can be misleading, and the doctors don't understand the way they signal at the moment. So there are some challenges here. Let's take a look at them in more detail. I made a list. Actually, I have 5 points that I wanted to discuss with you. These are the points where new chances will lie, I think, in the future. The first challenge is the problem formulation. You can think, well, what is the problem? To formulate a problem, it's just setting a question, right? But the challenge here is that we are engineers and we are talking to doctors. We have to learn to talk each other's language, and we have to learn, we engineers have to learn to really get the point of the people from another domain, of clinicians. What actually are they looking for? Getting back to this image uh, um, of of the cells, I can tell you that finding the exact contours is very intriguing and very interesting um, for an engineer. So let's make the most perfect contour possible. Let's put all cells with metastasis inside that contour, all cells outside. In practice, often, at least all applications I heard about for this kind of images, um, these lines are not needed. There is simply nothing that a doctor can do with them. But the doctors has to know if there is metastasis shown here in the image. He has to know which part of an image is affected. He may even want to know which percentage of the image is affected. But the exact cell here or there, that's not really what they need to have. There is simply no application in the clinical um, domain for this. The same is about finding the region where cancer lies. I mean, there are careers built on that. In practice, that region is normally not being used. That's also one of the reasons nothing is in the hospital, because the doctors, when they cut, they use so-called safe margins. They don't need the regions exactly. They have to cut much more for security. And for simply defining whether there is cancer or not, they need to take a biopsy. That's one point. That's not a contour, etc., etc. So there are many of points that the doctors have that we have to listen to, and I'm not sure that this process went well up to now. So guarding this process at least is very important. The next challenge is something that you consider probably to be like a normal thing. It's having a data set, finding a data set. Why is it a problem? Well, I do agree that we have a lot of digital data. Also, a lot of medical data is now digital. Those image making machines, they deliver now digital images. So there is no data starvation, etc. But when you look at an image of a dog, you know it's a dog. When you look at an image of a cat, you know it's a cat. When you want to have more of such images, you go to internet search engines, or you take databases already constructed for computer scientists, and you can have thousands of images with the right labels. If you have some images you don't have labels for, images of other animals or images of streets, etc. You can even make a game online where people are labeling these images, and when they provide occasionally the same label for the same image, you can say that label should be probably true. That's already a project of I think 15 years old in Carnegie Mellon University, when they launched such a public labeling system quite successfully. The issue with the medical imaging, and again, think about, for example, the macroscopic image, but doesn't matter if you look at MRI or any other, people cannot label these images without specialized education. So here we depend on a very small, relatively small amount of people to provide us those labels. These labels are not saved when the images are acquired. Saving and making these labels is simply at the moment not a part of clinical pathway, not a part of clinical procedure. So finding data sets, making data sets for our healthcare applications is still a challenge. Another challenge consists in having the suitable AI algorithms. I know there are many of them. I know also there is software where you can be creative, building or adjusting your own architecture, and plenty of experiments with deep learning. But I think we have to look further. We have to realize that only giving an image, it's not a solution for healthcare decision support. A doctor never looks only at one source of information. There are multiple sources he or she has to use in order to come to hopefully correct diagnosis. The machine will need them as well. So we need text, we need binary variables, we need questionnaire outcomes, we need images, we need longitudinal data as in the cases as it is available. So there is a multitude of data sources, different types, that we have to combine, and we have to think how. Is it still for one deep learning architecture? Is it for architecture of architectures? Is it how to choose the right way? We don't know yet. And yes, of course, there is research going on in this domain as well, but this will require more development, I think, especially when we also think about longitudinal medical data. The next challenge, it's just one word, but a very long story, explainability. So the doctor is the one who is responsible for the treatment, for anything that happens to the patient. Doctor carries the responsibility. The computer is there to help the doctor, not to substitute the doctor, but to help. It means that when the doctor looks at the screen with our outcomes, the doctor has to understand why we provide this input. If suddenly something changed in the format of the data we give to the computer, and the decision support starts to label every patient as a sick patient, in case of insight, in case of explainability, that can be seen. So the doctor will see that the decisions are made based on the wrong region of an image or something like that. So, of course, this is also a psychological problem, because I think after some time, doctors will believe more in the systems and will trust them. At the moment, we do have the issue of trust. Trusting in AI is not yet there, especially not in healthcare. And finally, the last challenge is last but not least, is that the universal applicability of the methodologies is needed. There are data sets on which something works, but if we go into reality, if we want to bring theory to practice, we will see that each hospital has a slightly different tradition, a slightly different acquisition, a slightly different protocol, and a slightly different format to store the data. So if we want to come with a smart system, that smart system must be quite universal. It must have kind of understanding for different hospital environments, for different systems for acquisition. So to conclude, what I want to say is decision support in healthcare obviously needs AI, and the progress will probably be brought mainly by smart applications of AI. There is a website online where, by coincidence, I've seen the picture that you can see here. That's a cloud of words, and that cloud was built based on my publication list. So I was a bit surprised, or well, at least was to be expected, but in any case, I could see very clearly the word detection there. Indeed, I did quite a lot of research to detect something that goes wrong in the healthcare domain. I think we will move from detection to prediction. So we want to be able to say to the patient what will happen to him. We want to say to the patient that he's developing Parkinson's disease before he has very clear, obvious symptoms, and then they are more difficult to deal with, to go on with the treatment. So we want to be in advance, and I think that's also something we want to predict sepsis and not let it develop until we have to detect it. So there are many cases when we want to predict and not to detect. And obviously we have to move from lab to practice, and I think the time is right for that, and I'm working in a couple of projects where we hope very much to reach that point. So we can see that there are quite some challenges. That also means that there are quite some solutions to come, and we can contribute to them. I would like to thank you all.
Thank you for watching this WIS Conference 2022 video from Maastricht. And you're welcome to watch more conference videos from WIS worldwide on YouTube.